first of all, this idea of a chi-squared probability density function, which, as you'll notice, has a positive skew to it, and it never is negative. One important feature of this particular probability density function, PDF, is that it requires something that's called the degrees of freedom. I'll be showing you how to determine what those are from the table of data. How are we going to use this particular distribution? It will be for a test of statistical independence. So I'm going to give you an example here very quickly using playing cards to understand this concept of independence. We've seen this before, but take a quick review now here. If we're looking at the relationship between two variables. Let's call it variable A and variable B. So let's say we know the value of variable A, it's a queen. Does that help us to predict the specific suit, whether it's a spade, diamonds, club, or hearts? Well, as we can see, knowing it's a queen doesn't help you to know which specific suit it is, so we say that these two variables, the value of the card versus the specific suit, are two independent variables. Consider this other possibility, two variables A and B, but this time it's the color of the card. Does that help us to predict a specific suit? Well, in this case, it does, because we can say that if I know it's a red card, it can't be a spade or a club. It has to be a diamond or a heart. It doesn't help us to know exactly what the suit will be, but we use this information to be able to predict help us to predict what the suit will be. So in this case, we say the two variables are not independent. Knowing one helps to predict the other. So independence means knowing the value of one variable doesn't help to predict the other. Not independent means that it's useful information, because now we can adjust our prediction of what the other variable is. Little note for future reference is that if two variables are independent, then it means that they can have no connection, there is no correlation, and there is no causality. But we're going to see this later. So let's take a quick example, some examples of this idea of connecting two variables in some way. For example, person's mother tongue and their province of birth, or the nationality, the citizenship of a person, and religion. Political party and the language that somebody speaks. The eye color, somebody's color of eyes versus the country of birth. We could also look at a combination of variables that are quantitative and qualitative. These first examples above are qualitative variables, categorical. The ones down below are quantitative variables, how tall a person is and their income, the number of hours you slept last night, the exam results. And of course, then we can have a mix of these two. These are many examples, and there's many, many others, where we're looking at the connection between two variables. Specifically, the chi-squared test is for qualitative variables. But as we can see, there's ways to adjust this to account for quantitative variables as well. So, the test of independence, chi-squared test, is specifically for qualitative variables. Let's take a quick example. The eye color and the person the continent where the person was born. What we'll be doing is collecting data, for example, person's eye color, blue, green, and so on, and also what continent they were born on. You'll notice that these are completely arbitrary. I can put variable B on the right-hand side, variable A across the top. We'll collect data, which leads to a chi-squared table. We'll be seeing what this means, how it's done. And as I said, it's usually for qualitative variables, but there's a way to take quantitative variables and convert them to qualitative by making them, in effect, ordinal variables. For example, somebody's height could be arbitrarily decided being short, average, or tall. And in addition, this could even work for dichotomic variables as well. Basically, the table of data will be used to determine the degrees of freedom necessary for the chi-squared PDF, and then secondly, to calculate a specific statistic, which we'll refer to as the chi-squared statistic. How does the test performed? Well, here I've got an example where I've got the PDF of a chi-squared. Let's say the degrees of freedom are equal to 6. The area below the graph, of course, is 100%. And let's say I use the data and, for example, I calculate this chi-squared statistic and it's equal to 11.4. We will then place it on the graph, and we know that, for example, area has to add up to 100%. So for example, the area on the left is 82.2%, completely arbitrary, these numbers I'm giving, although they would come from the table. It has to be 17.8%, for example, on the other side. This area to the right is sometimes referred to as the significance level. It's also known as the PROB value or the p-value. Let's take a look at this idea a little bit further. And I'll do this with, first of all, the classical approach to conducting this test. First, use the table of data to determine the degrees of freedom. Then, second point is to determine in advance the significance level. So, for example, I set this arbitrarily at 15%, and then I have to look up the table to find out if the critical chi-squared, what is that equal to? From then, I'll be able to accept or reject the null hypothesis conducting the test. So in the case of a classical approach, we predetermine the significance level, the area to the right, and then we use the table to determine the critical chi-squared number. There's another way of doing this test, which is referred to as the PROB value approach. Once again, I'm going to stick with the degrees of freedom, for example, equal to 6. We'll use that from the table. Next is we'll calculate from the data a test statistic. Let's say, for example, it's 8.7. In which case now, I'll have to determine the PROB value or the p-value. We can use that, the table, to do that. So in the case of a PROB value, we have a test statistic and we calculate the PROB value. In the classical test, we predetermine the significance level and then determine the chi-squared statistic. A little bit of advice here. If you're doing it the PROB value approach, you'll be looking at the top row in the stat table to find the p-value, or what would otherwise be known as the significance level.